draw a burette and a flask. Yes? Okay, and in general, your sodium hydroxide is in your burette, and your nitric acid and your phenolphthalein is in your flask, right? Yes?
Whenever you use titration, is the base usually going to be in there?
It usually is. It doesn't have to be, but oftentimes it is, the base in there. Okay? And then we have other titrations that are like redox titrations. In fact, Ulissa goes over to Grayson and is in like the vet tech program. She said, we were doing a redox titration yesterday. It was really kind of cool. So, so sometimes other stuff, but yeah, usually that's it seems to be pretty much the setup. Okay, now, if we take a magic school bus ride and get a molecular view, tell me what this sodium hydroxide looks like. Okay, so the Na plus is separated from the OH minus? Yeah. Okay, good. And you know what? If you look at your ionic equation, that's exactly what we did. It doesn't exist together, okay? What else is present in here if you wanted to include it? There's water. This is a solution, okay? Some of you might not have included it, and a lot of times the water's not what we're focusing on, so it's okay if you left it out, but this is the medium in which everything's floating around, okay? Tell me about the HNO3. How does that look? Does everybody agree that we're going to separate these? Okay, again, it kind of conforms with the ionic equation. What else is present in here? There's some water as well, if you wanted to draw it. Did anybody, how many people included water? Did anybody get really fancy and kind of draw your water to where you showed that the negative ends were close to the positive ion and the positive part of water was close to the nitrate? Anybody get fancy? Okay. All right. That's just getting fancy, not necessary, okay, but just kind of interesting. Okay, and of course we have phenolphthalein in there, but that's a complicated molecule we're not going to attempt to draw. Okay? All right. So this is before. Okay? Now, during. We've got our burette. It's going to deliver some sodium hydroxide into our flask. Okay, remember, this was Na plus and OH minus. This was H plus and NO3 minus. Yeah, there's a little bit of water in there. Okay, now, what's going to happen when this Na plus and this OH minus starts to enter the nitric acid? It forms water. Look at this react. The whole thing was about forming water, right? If you look at net ionic, even if you look at this, we form water. So should we definitely write water here?
Yes.
Yes, even if you didn't include it before, you should definitely have waters here. Now I'm going to include a few so that it looks, we can tell some is being made. Is there H plus floating around?
Yeah.
Yeah. Is there nitrate floating around? Is there anything else? Okay. I hear Na. I'm going to make more room because I didn't plan ahead. Okay. So I've got Na plus and I've heard OH minus. Is this correct?
The OH, it goes with the H.
Okay. The OH is not correct for this. Okay. Because have we added a whole bunch of OH? Or are we adding it in small bits, drop by drop by drop? So if we're not at our end point yet, what do we have more of, acid or base? We have more acid. Every time an OH interacts with an H+, it turns into water. So there actually is no free-floating OH in here. Is there still free-floating H+? Yeah, we started with a lot of acid, and we're adding drop by drop by drop. We're adding little bits of base. So this is in excess, and this is limiting. We're limiting the amount we're putting in. Does that make sense? Okay, that's what's really important. I'm looking for the absence of hydroxide here, but yes, there's some sodium in here, because that just hangs out, right? Okay? All right, now, when we get to the equivalence point, and you guys need to help me out, what is the definition of equivalence point?
When it's neutralized.
When it's neutralized, what's another way to say that? The acid and the base are balanced. In this case, the pH will be 7 because we've got a strong acid and a strong base. Okay? I guess I should change this back to our original reaction. Okay? And this is what I want to say though. Oh, maybe I needed that for a second. Equivalence means you have an equivalent amount of your H plus and your OH minus. In this case, what's the equivalent amount? 1 to 1. If we had had HNO3 and calcium hydroxide, when we balance this, what would we have gotten in front of the HNO3?
2.
We said that before. We would have had a 2. Okay? So, will an equivalent amount in this case be 1 mole of calcium hydroxide and 1 mole of acid?
No.
No. In order to have exactly the same equivalent amount of hydroxides and H pluses, for every 1 mole of base, you would need 2 moles of acid. Or for every 1 mole of acid, you would need a half, right? A mole of base. So equivalence takes into account the balancing, but it will be the exact right amount of H plus and hydroxide. Okay? Now, here's my question. At the equivalence point, do you have, let's write down all the possibilities. I guess we should write that we have phenol, blah, 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 blah. Will you have H plus?
No.
Why not?
Because they all water.
Because if you have an equivalent amount of this and what else? OH, will they still exist as opposite ions? No. What are they going to exist as?
Water.
Water. So these are not there. They have combined. That's what's going on in this reaction. Okay? So I'm going to erase these, clean it up. Okay? And I'm actually going to put in some more waters just to kind of drive home that point. Will we have nitrate ions?
Yeah.
Yeah. Nothing ever happened to the nitrate. It's a spectator. Everybody left it alone. Will we have sodium ions?
Yes.
Yes. Okay. Now, we have phenolphthalein. Is this pink?
No.
Not pink. Was this pink? Not pink. Was this pink?
No.
Not pink. Okay. How do we get the pink?
Basics.
Oh, this is the end point. So, what do we have to add?
More base than acid.
Right. We have to add a smidge, we have to add another drop of sodium hydroxide, right? So if to this we had water, we had nitrate, we had sodium, bunches of waters. If we add a little bit and we get hydroxide, now will this be pink?
Yes.
Yes. And there you have it. Now let me ask you this question. If we use an indicator to tell us when to stop titrating, are we going to calculate the exact molarity of our acid?
No.
No. Will we be a little bit too low or too high?
Too high.
We'll actually be a little bit too high. Let's go back to MAVA equals MBVB. What is a little bit too high here? The volume of the base, right? So if that goes up, how will that affect our molarity? And it's directly proportional. If you have more moles of base, doesn't that indicate that you had more moles of acid to neutralize? So if this is too high, then we would end up calculating a molarity of acid that's slightly too high. Now, if you have a faint enough pink, a lot of times that error is negligible. And it must be, because after all these years, we still tend to use that strategy. Can anybody think of another way to tell that we're done so that we wouldn't have to do the indicator and go slightly past? Can anybody think of something else we might use? I heard someone say pH. Is that what you were saying, Star?
Well, I said
Litmus paper, right. And so, like Tiffany, you said the pH would be 7, right? In this case, yes, it would be exactly 7. So if during your titration, you could read the pH all along, what would the pH be here? Before you started. You're going to put your pH meter right in here. Really low, because it's acidic. What would your pH be here? Still low, but getting closer to 7, right? What would your pH be here?
7.
Exactly 7. And the pH here, if you went past, would be a little bit above. So if you could watch your pH and very carefully stop right at 7, then you could use this. It might be a little bit more accurate. But you know what? pH meters have their own error built in. And so sometimes after all these years, I don't know that anybody has determined that it's worth it to do that. We kind of do both. We use pH, we use indicators. But does that make sense?